Click the bell icon to get latest videos from Ekeeda.
Hello friends, in last video we have seen the basic principles that are used in machine design. In today's session we are going to look at the modes of failure and the factor of safety. Modes of failure of any machine design part or any mechanical part or system. Guys, there are many ways a machine can fail. You'll say why we are talking about the failure, because we are most concerned about the safety. Guys, machine design is the only field where you have to consider the failure first and after the success, because we have to avoid the failure. In order to avoid the failure, you must know what are the ways of failure. So in today's session, we are going to look at these different and important types of modes of failure of machines or machine parts. So let us begin. As you can see, the very first type is normal stresses. Normal stresses are induced resistance given to the applied forces, or these are the intensities which are produced against the applied forces. Now there are two ways your normal stresses will be induced. Either your stresses will be induced in tensile manner or they will induce in compressive manner. So friends, we know that tensile stresses are induced when the body is subjected to pull forces, means body is subjected to elongation of that particular part, right? And compressive stresses are induced when the body is being compressed, means the body is being contracted by the applied forces. So it is the opposition to the tension and it is opposition to the compression, which is nothing but your tensile stresses and compressive stresses. Now, a body can fail in a normal manner. So, when the surface area on which the force is acting is perpendicular to that particular force direction, they will be called normal stresses. Like we said, first type is of stress, tensile stress, second is of compressive stress. So, in case of tensile stress, if this material is not sufficient to carry the forces which are applied on it in pull manner, then the body will fail. Or if the material is not sufficient to carry the compressive forces which are acting on them, which are push forces, in such cases I will call, or we will call, that the material is fail in tension or the material is fail in compression. So this is the very first and basic mode of failure which we consider almost everywhere, almost in each and every part which is subjected to loading. As you can see, the second type is shear stresses. As we know that shear happens when two successive planes try to slide against each other. In such a case, when the separation happens between two successive planes, the failure is called shear failure. And the stress which is responsible for this, or the stress which is generated while this shear happens, is called shear stress. So second mode of failure is shear failure. The third type, let us move to the third type, that is called a rupture. Now, rupture happens when something is, when a body is subjected to loads in such a manner that the body will be destroyed in uneven manner. Like if a hammer is objected on certain small object, or the hammer is pulled or piled on some small object, the object will destroy in an uneven manner. You can't decide whether it is failing in compression or whether it is tension, whether it is shear. In such a case, that the body is failed in the rupture. So that is our third mode of failure. The fourth mode of failure you can see is tearing. Tearing, we know, we tear the page, we tear the thin sheets. So in such a manner where the particle or the object or the thin sheet lamina which fails in two separate parts, but application of forces in parallel manner to the plane of failure, it's called tearing. The best example is tearing of page. We can demonstrate it in simple manner. A page which we have kept in this way, there is a line along which I want to tear it off. I'll apply the forces in parallel manner only to these lines. The only thing is the nature and the direction of forces will be different. Can you see this object is failing along the line? So this particular phenomenon is called tearing. So this is just another way of failure of the object. Let's move ahead. Buckling. So guys, next type is buckling. Guys, we have already learned this topic in strength of materials. Buckling of columns and struts. So something or some part which has its length larger than its lateral dimensions. For example, the length is larger than its diameter. There are chances that if axial forces are applied on such object, it will buckle. Buckling is nothing but bending of the things in vertical manner. Generally, we consider bending of beams, but bending of the things which have length in a y direction after application of axial loads is called buckling. So there is another way where things can buckle. Now huge shafts which are vertical in manner can buckle, right? So that's another way of failure. Our next type is bending. Quite obvious, beams are the members which are subjected to bending after application of transverse loading. Yes, so this is the another way of failure where in bending not only deflection will be larger but also the bending stresses will be induced. Our last topic or the last type of failure is fatigue. Now fatigue is called the deadliest failure manner because in case of cyclic loadings, what are the cyclic loadings? When some object or the part is subjected to loadings which continue for n number of cycles or which come back to the object after equal interval of time are called cyclic loading. For example, a wristwatch, there are many gears in the wristwatch. When they work, when they function, they perform some cyclic motion or the oscillating motion. So they undergo cyclic loading situations. The parts, the objects which undergo such kind of situation, the cyclic loading, they may fail in fatigue because during the cyclic loading their plastic deformation keeps on happening. The problem is due to the machine is running, we can't identify, we can't trace these plastic deformations. So at certain point it fails in fatigue. That means it fails without any prior identification or without any prior information. So all such kind of failures are called fatigue failures. Guys, in today's session we have seen so far are the modes of failure. There are different modes of failure, so there are different ways in which the loadings that happen on the product. So guys, remember forever whenever you go for the designing of a machine element, very first thing you have to look at is the mode of failure of different objects in different manner. Once your mode of failure is decided for that particular topic or particular product, you can decide the design method for that particular product. Let us move ahead and let us look at the last part of this topic, that is factor of safety. Guys, factor of safety is something we can call as the margin. Let us say we have purchased a water bottle. It has the real capacity of 5 liters, right? But instruction, if it is written that just pour in 1.4 liter or just pour in 4 liters of water inside it. So why that 1 liter margin is given? Guys, though the bottle is designed to carry 5 liters, it is desired, according to the manufacturer, it is desired to pour in only 4 liters of water. So that 1 liter margin is nothing but your factor of safety. Yes guys, the extra margin we must give. And why that margin is required? Guys, when we design some product, we consider some boundary conditions. We apply some constraint to that design. We assume that the product is going to sustain or the product is going to experience these conditions. But that is not always the case. For example, if you design a product to carry the tensile stresses, of course, the loads are acting in the normal manner in that case, but somehow by any chance the loads act in shear manner. That means the loads act in perpendicular manner. In that case, not only the tensile stresses but also the shear stresses will be induced in that product. But our product is designed only to carry tensile stresses. So that inclusion of shear stresses may fail the product. So in such cases where you have even a slight idea whether apart from normal stresses, shear stresses may also come into picture, you have to design it with certain margin so that the product will not fail. Second example I'll give. If you design a product to carry 10 Newton of force, but somehow by some means the load act on it is actually 15 Newton, in that case the product is going to fail. So when you have even a slight idea that the force actually is going to act will be having some slightly larger magnitude than the design value, in such case you have to design it in some over manner so that even after 15 Newton of force is acted on it by mistake, the product will not fail. Yes, so that was the basic idea of factor of safety. Let us look at it properly. Guys, the types of stresses, of course we have already seen the types of stresses. One of the stress strain curve I will draw like this. And the second one like this. This is the stress, sorry, this is the stress and this is the strain. The stress and strain. Can you identify this one? Yes, you are right. This is the stress strain curve for ductile materials. And this one is for brittle materials. Of course, we have learned this. We know the salient points also, the important points also of this curve. Of course, this is the starting point, this is the point of elastic limit, this is upper yield point, this is lower yield point, this is ultimate point, and this is breaking point for any ductile material. Whereas in brittle material, yes, there is some elastic point, and beyond that, you can't have distinguishing points. So, what you have is ultimate point and the breaking point. So, I'll call it breaking BR point, ultimate U point, and this is elastic point. Whereas here we have elastic point, upper yield point, lower yield point, ultimate point, and breaking point, again BR point. Guys, when the things are designed, these stresses are taken into consideration to certain extent. Yes, the yield points and the ultimate points. Now guys, you need to understand this thing, very important. See, whatever we design, they actually undergo different forces. When they undergo forces, stresses induce in them. Stress can be shear stress, it can be a tensile stress, and can be a compressive stress. Similar stress strain diagrams are used for their analysis. Now, when I say my object has reached its elastic point, I have the chances, if I remove the load which is acting right now on the product, it will trace the same line back to the origin and it will regain its original shape, because the section which lies up to this is called elastic section or elastic region. The region thereafter is called plastic region. Now, what do we mean by elastic region? When your object is stretched or it is elongated or it is compressed till the elastic region, there are chances it will regain its original shape and size. But once it starts going ahead of it, it actually goes into its plastic deformation area. What does it mean? At certain points after this elastic point, if I start reducing the load on the body, it will not trace the exact curve back to its original shape. That means it will come to certain shape like this. So can I say this small amount of permanent deformation is there? Yes, it is called plastic deformation. So we can conclude that after elastic point, there will be always some plastic deformation retained inside the body. This plastic deformation goes on increasing as we goes on increasing the force applied. So one thing is very clear, that after elastic point or after yield point, it is impossible for the material to regain its original shape and size. Guys, if we keep on adding this kind of forces which introduce the stresses which are greater than upper yield point, the body is going to experience the permanent plastic deformation, which in other way going to help only failure of the product, not other productive thing. We don't want the failure of the product, so that we should consider that the only possible stresses are only up to this, which is up to yield point. Guys, when we design a ductile material, we'll consider that the material or the body or the particular part will have only limitation, that is sigma of upper yield point. Means we consider this as the extreme stress that the material can handle, whereas it can handle up to the ultimate stress. We'll consider that this is the extreme end, and we will design the product in this manner only. That is first thing. But when we switch back to brittle stresses, it's not that simple. Brittle stresses somewhat show the elastic point, but thereafter they don't give us the significant points like upper yield point, lower yield point. They directly give us the ultimate stresses and then breaking stress. So in case of brittle material, I have to consider ultimate stress as the reference point. So I'll consider that I can apply the forces on brittle material or brittle element to the extent of ultimate stress. Can you see the distinguishing thing? Yes, for ductile materials, my maximum possible stress is upper yield stress, and for my brittle, it is ultimate stress. Now, when I consider these two stresses, what I'm supposed to do is, guys, we know that these two things are nothing but the extremities, that are the maximum possible stresses a material can handle. So, what is factor of safety? Factor of safety is a ratio of ideal to the actual. So that ideal is the possible extreme end, so I'll say extreme value divided by actual value. We know that extreme value is always greater than the actual value. So in such case, factor of safety is always greater than 1. Guys, always remember this thing. This is very important thing. Your factor of safety is always greater than 1. So factor of safety should be greater than 1. That is one condition. Now we have seen that the extreme ends or extreme values for ductile and the brittle materials are different. That means the factor of safety formula will be different for both of them. So in case of ductile material and in case of brittle material, factor of safety is equal to extreme value that we use in ductile material is its upper limit, sigma upper yield. That means stress that is induced at the upper yield point divided by actual value. So I'll call it working stress. Whereas in case of brittle material, FOS will be defined by extreme value of brittle, which is ultimate, sigma ultimate, divided by actual value. This value also I'll call working value. That's it. Factor of safety. So these are the formulae we use for factor of safety. But what do we find out in that case? There are two ways you can use this concept. If you already know, see guys, we already know what is ultimate yield point for a material, and we already know what is ultimate point or ultimate stress point for a material. We need to know the sigma working, that is the maximum stress that can be induced in the part or in the object. Once we know these two things, we can find out factor of safety. But guys, the working stress generally is experienced by the product. It's not a defined thing, because empirical formulae sometimes fail in deciding the actual stress that is going to be induced. So in such a case, that you have to work with factor of safety. Guys, these are the things of experience and judgment. Through judgment, we can suggest the factor of safety required for that particular product or for that particular element. So as of now, we have the values with us of ultimate yield point or upper yield point and factor of safety. Now using these two ratios, I can definitely find out sigma working, so that I will define the extreme value that the stress can be induced in the body, so that with the margin of factor of safety, my body will be kept safe. The same thing we can apply here. We already know sigma ultimate for brittle. We, through our experience, already know what is factor of safety for brittle material. We can find out the value of sigma working using these two relations. So what is my purpose? My purpose is to find out sigma working first and then design the product accordingly. Or if the product is already designed where I know sigma working, I can define factor of safety. For example, if my machine is capable of carrying 100 Newton, but when I specify the specification of this particular product, I'll say maximum capacity is only 50 Newton. In that case, my FOS becomes the maximum possible extreme, which is 100, divided by the maximum working, which is specified, which is 50. So in this case, it becomes 2. Now guys, you will say you are not talking about stresses, you are talking about forces. As we know that stress is directly proportional with the force, and hence factor of safety can be defined in terms of forces as well as of loads and stresses. So FOS can be specified as extreme force divided by working force. Or it can be defined as extreme stress divided by working stress. Now, the same thing is applicable not only for brittle but also for ductile materials. Now, there are some specified factor of safeties which are predetermined by the agencies and they are taught. Of course, we are going to look at them at the time we are going to solve the problems, we are going to solve the numericals of machine design. So, let me conclude this topic. We looked at different types of failures. They can be failure in shear, failure in normal and tensile stresses, even compressive stresses, failure in buckling, failure in bending, the tearing failure, the fatigue failure, etc. We also looked at the thing that the failure modes are important while designing the products. The next thing we looked at is factor of safety. We went through the definition of factor of safety. We looked at the expression of factor of safety, and then we defined the factor of safety expressions not only for ductile but also for brittle materials. Now the same concept we are going to use while solving numericals on machine design. So that was for this particular topic. Thank you so much for watching the video. If you like this video, please subscribe to Ekeeda. Thank you. See you.